Welcome. This is Geometry A, Unit 8, Lesson 13. Unit 8 is a long unit. Today we're dealing with the altitude drawn from the right angle of a right triangle. And I've got the situation drawn below. We have right triangle ABC, where C is a right angle, and we draw an altitude. That means a line drawn from the vertex so that it is perpendicular to the opposite side. So CD is perpendicular to AB. And angle CDA and angle CDB are right angles. Okay. Now this divides the triangle, and it's not obvious at first glance, into actually three similar triangles. Let me see if I can outline them for you. We have this, let's make a new layer. Let me go with yellow. So we've got this medium-sized triangle, and actually let me go from large to small. We've got the original triangle right there, and I'm going to redraw it over here. The original triangle. Then we've got the medium-sized triangle, and I'm going to flip it around and rotate it. And we've got the small triangle right here. Small triangle right here. And so the idea here is this, that triangle, let's see if I can map out which angles are what. Angle A, angle B, angle C, angle C, no, this is angle A, angle D, angle C. Okay, I'm going small angle, medium, right angle, medium angle. Small angle, angle B, nope, angle C, and I'm looking at the BD. So you can see that triangle ACB is similar to triangle ADC is similar to triangle CDB. Okay? And that's the big aha moment, that there are three similar triangles, the original large triangle, the medium triangle, and the small triangle. And you can see that the red triangle is similar to the orange triangle by rotation. You have to rotate and dilate. But you'd also have to do a reflection and a rotation with both of those to get to the original large triangle. Okay? But I'm going to go through a little bit of theory. The lesson proves the Pythagorean theorem using this theorem, but it also doesn't provide a detailed proof, but somewhat proves the theorem itself. And so I'm going to go through a little bit of theory at first, but I'll get back down to the practical problem-solving presentation later in the video. So let's go into kind of a proof of why this works. Okay, and so let me get rid of this layer here. Glad I made another layer, and I'm going to make another layer as well. Okay, so first of all, these are all right triangles. So we were given right triangle ABC with C a right angle. Actually, I'm just going to do it this way. C a right angle. There we go. Okay. And altitude CD. Okay, so we know these right angles. We know angle ACB and angle ADC and angle BDC are all right angles. Let me use the symbol for right angle. Right angles. Okay? By definition. And by definition of right triangle, in the case of angle C there, by definition of altitude for the angle D's, right? Okay. Likewise, through the reflexive property, angle A is congruent to angle A. So angle A is congruent to itself. And angle B is congruent to angle B. Angle B is congruent to angle B by the reflexive property. Okay, so check it out. Let's go with the large triangle CAB. Triangle CAB is similar to, now I went with right angle, small angle, medium angle. So I'm going to go with right angle D, small angle A, C. So triangle DAC. By angle, angle. Okay, and I can also say the large triangle CAB is similar to triangle CAB, that's right angle, small angle, medium angle. So to the small triangle, right angle, medium angle, right angle, small angle, medium angle, DCB. DCB by the angle-angle similarity postulate. Notice they're both similar to CAB. They're both similar to CAB, the large triangle. So therefore, they are similar to each other because there is a transitive property of similar triangles. So triangle CAB, or DAC, is similar to triangle DCB by the transitive property of similar triangles. Two triangles similar to the same triangle are similar to each other. Okay, so that proves the relationship we found, that we have three similar triangles. Now the trick, as I said before, is keeping them straight. Now for the proof of the Pythagorean theorem. Proof of the Pythagorean theorem. If the triangles are similar, then the ratio of their sides are similar, right? So let's label some things. X, Y, A, B. Okay? And here we go. We were given, and I'm just going to say we were given the drawing. Just to be inclusive of all the stuff that we said there. Okay, using the theorem, the altitude of a right triangle theorem that we just demonstrated or proved, I'm going to say that A is to X. Now note that is hypotenuse is to long leg, as the hypotenuse, which I'm going to call C of the large triangle, to the long leg of the large triangle. C is to A. Notice the way I'm doing this here. I'm trying to name the sides by their properties. I'm saying that A is to X. A is the hypotenuse of the medium triangle. X is the long leg of the medium triangle. So that's hypotenuse to long leg. So on the large triangle, the ratio that would be the same is hypotenuse to long leg, C to A. Okay, and let's go with this one. B is to Y. B is to Y. That's hypotenuse is to short leg of the small triangle, as hypotenuse of the large triangle is to short leg of the long triangle. C is to B. Okay. Cross multiply, A squared equals CX, and B squared equals CY. Just so you see what I'm doing here, I'm cross multiplying. A squared equals CX, B squared equals CY. doing the cross products. Cross products are equal in a proportion. Okay, now I'm going to add these two equations together. A squared plus b squared now equals cx plus cy. Cx plus cy. Note I can factor out c, x plus y, and then x plus y happens to be c by segment addition. A squared plus b squared equals c times c, and then c times c is c squared. A squared plus b squared equals c squared. We have just proven the Pythagorean theorem. This was by addition, the addition property of equality. This is by the distributive property, which is factoring. Distributive. Okay, and this is by multiplication or squaring or squared, the definition of squared. Okay, and that was substitution actually right there. Oh no, that was segment addition. Segment addition. And definition of squared. There we go, QED. Quod erat demonstrandum. I said it, therefore I proved it. All right, so that said, let's go to some practical problems. Okay, your problems are going to center around finding missing sides. And let me get rid of this and prove one more thing here. Let's say I label this x and this y, and I'm interested in this dimension right here. Let's write and solve a proportion here. Okay, I'm going to say CD is to x. Now CD is the short leg, x is the long leg. As on the small triangle, short leg y is to long leg CD. Okay. Short leg is to long leg CD. Cross multiply, you get CD times CD or CD squared equals XY. And now square root both sides, and we find that CD equals the square root of XY. This is something known as the geometric mean. Geometric mean. That is, you multiply and take the square root. Let me show you how it's used. Okay, if you know two lengths, and I happen to know two lengths on here because I drew it this way, 1, 2, 3, 4, 5, 6, 7, 8, that this length of the hypotenuse is 8, and this length of the hypotenuse is 3. And I want to find the length of CD, or the altitude. All I need to do is this. Multiply 8 times 3 and take the square root. 8 times 3 is 24. Okay, and 24 is 4 times 6, so you could say 2 root 6 if you wanted to, or you could approximate it using a calculator. Square root of 24 is going to be like 4.9, because square root of 25 is 5 exactly. All right, so that's the way you use the geometric mean. You're going to get several questions like that, where you have the geometric, you want to find the altitude, and you're given the hypotenuse divided into two segments. But what about some other more complicated scenarios? The trick is keeping things straight as to what's what. I've been using naming of sides: short leg, long leg, hypotenuse. And it can help to draw the triangles out separately, and I'm going to demonstrate doing that. Let's say I tell you this length is 3, and let's tell you this length is 1, 2, 3, 4. Let's say this length is 5.5. And we want to find all the other missing sides, missing lengths. Okay, maybe I want to find this side right here, x. Okay. Don't forget you have the Pythagorean theorem at your disposal as well. So if I get two legs of a right triangle, I can find the third leg by square rooting, or squaring, adding, and square rooting. That is that this length now, AB, is x squared plus 5.5 squared square root. There's that. Okay. But let's go back to what I was talking about, drawing out the triangles separately here. Let's go ahead and do this. Let's draw out the large triangle and label the vertices. Label the vertices. Small angle, right angle, medium angle, ACB, small angle, right angle, medium angle. Okay, and then we've got a medium triangle. Okay, and we've got right here, we'll draw it right here in the same orientation so we can clearly see how things are. Small angle, right angle, medium angle, ADC. Okay, and then small triangle. Small angle, right angle, medium angle, small angle CDB. And let's label what we know. What do we know? Okay, we know x is AC. So x is here and here. We know BC is 5.5. 5.5, which is here and here. 5.5. Okay, and we know DB is 3. Okay, now anything I can use to find a missing part here, to find x, it would be really cool if I could write something with the hypotenuse. And I don't have anything right away, but I can do something in multiple steps here. For example, 5.5 and 3 are two sides of a right triangle. I can use that to find the third side. So let's find CD here. CD is the square root of 5.5 squared. 5.5 squared minus 3 squared. Okay? And let me put that back in place. Square root 5.5 squared minus 3 squared, using the Pythagorean theorem. Okay, and now I can write a ratio between the two triangles here. Let's do this. Let's do 5.5 is actually not 5.5. Let's do 5.5 squared minus 3 squared is to x. That's 3 is to 5.5. Okay, so we can write that out. 5.5 squared minus 3 squared, square root, is to x as 3 is to 5.5. Okay, cross multiply and divide. Now here's a little bit of a trick. Multiply the diagonal that x isn't on and divide by the remaining side. So x is 5.5 times square root 5.5 squared minus 3 squared over 3. And we can find x that way. Okay, and so here we go. Desmos, oh Desmos. Desmos, who's the Desmos? And you can enter this expression just as it's written, 5.5 square root SQRT, 5.5 squared, right arrow, minus 3 squared. So hold down Shift and left arrow to select it all, or click and drag to select it all, over 3. Okay, and we get 8.45. X is approximately 8.45. And always check to make sure it makes sense. This is 8, so that's longer than 8, so it definitely makes sense here. All right. Okay. So drawing the triangle side by side and labeling what you know can often help you to write a proportion. Don't forget the Pythagorean theorem. If you know two sides of a right triangle, you can use that to find the third side, and then write a proportion and solve a proportion, cross, multiply, and divide.